So, power rule, the derivative of x to n, where n here is some sort of number. It's our, it's a constant. It doesn't have to be a whole number, but it's a constant. Whenever we are taking the derivative of something raised to a power, in symbols, your rule to do this here is to multiply out front by whatever that exponent is. So our n is right here. And then subtract 1 from the exponent, right? So whenever we did the power rule worksheet, in some shape or form, that should have been your rule, right? Some of you wrote it out in words. Some of you may not have. But this is what we call the power rule. It's just that shortcut for taking the derivative of something that has just a polynomial function, right? X to a certain power, okay? So these first ones should be super simple. Zach, what would the derivative for number 1 be?
3x squared.
Good. Okay. And Bo, what about for number 2? Perfect. Okay, so hopefully we're all doing pretty well with that. Pretty straightforward. Multiply out front, subtract 1 from your exponent. I told you guys I taught Hunter how to do this a couple years ago, just because he likes to do stuff like that. Sometimes he has no idea what a derivative is and cannot do calculus, I'm sure he's forgotten it by now because it meant nothing to him. But we could train really any third grader that knows their multiplication tables pretty well to do this, right? It's pretty simple. But we will not be doing all problems where this is the only thing that we need to do. Plus, you guys need to have an actual understanding of what's going on instead of just the ability to do this. So the constant rule, these are just a couple rules here that apply to this. Constant rule, I showed you guys the other day. Really, you already know this. If you're taking the derivative of a constant, any number, 7, 10, negative 42, 3.897 pi, any constant, its derivative is 0. Okay? If we think about it, that's because if I have any number, it doesn't even matter. It could be like 3 pi, right? If f of x equals 3 pi, that's just a number, right? Even though it has a pi there, it's just a number. How many x's does it have with it? 0, right? So you are multiplying 3 pi times 0, which would be 0, x to the negative 1, but 0 times the negative 1 is just 0. So it's the same rule. It's just going to be, more simple if we think about it as that constant always equaling 0. Other properties of derivatives, if you have a scalar multiple, which we really have already done, if you have 2 times f of x, when you take the derivative of 2 times f of x, that 2 is just going to be multiplied by whatever the derivative is. Okay? We already really did that because right here we had that 4. So really when we took this derivative, it could have been like this 4 times, and then we could have just taken the derivative of the x to the 5th. That'd be 5x to the 4th. And then after that, you multiply the 20x to the 4th. So we really have already done that because we're just, instead of writing it out this way, we're just multiplying by the constant that's already there, right? So we've really already done that. And we have actually already done this. The derivative of things that are added or subtracted from each other, you can just take the derivative of them separately. So we really have already done that whenever we were doing problems like we did on the warm-up. So if we take the derivative of 3x to the 4th minus 6x squared plus 3x minus 1, we just take the derivative of each term separately because they're separated out by plus or minus signs, right? So, Hallie, what would we get for the derivative on that first one there? Perfect. Yeah, and it's probably different. I fixed the notes, but I didn't fix the copy. It's on that same slide. Okay, good. All right, Cade, what about number 2?
45x to the 4 minus 6x squared plus 6.
Okay, we're all okay here? All right, now, whenever we get a problem like number 3, I don't have just x to a power. I've got 1 over x to a power. So before I can take the derivative, I have to rewrite this so it's just as x to the power. So Maddox, how would I rewrite that? We can do x to the negative 5th. So if you have something in the denominator, you can pull it up and make it have a negative exponent. Okay. Now, if I want to take the derivative, because this just has a y right here, there's a couple ways that you can denote that you're taking the derivative. You can do y prime, or you can do this dy over dx. Either one of those notations are fine. You do not have to put both of them. I'm just giving you both of them because you may see either one of them. So, Maddox, whenever we take this derivative, what do we get? Negative 5x to the negative 6. Be careful, my mind there wants to say negative 4 because you're decreasing. But really, if you're doing negative 5 minus 1, you're going to get negative 6, right? So be really careful when you get those negative exponents. Students mess that up a lot. And your answer may be left like this, or it might look like this, negative 5 over x to the positive 6. They might move that negative exponent back down to the bottom. Either one is fine. I do not care which one you leave. But if it ends up being multiple choice, you need to be prepared. Either one of those could be there. We okay on number 3? All right. For number 4, I've got the cube root of x. I cannot take the derivative of a cube root, but if I write it with fractional exponents, I can take its derivative. So Wesley, how can we write that so that it's just x to a power? Okay, so the way that it works for roots, our rule for roots, is this. Whatever your, I'm going to call it r right here for root, if you've got x to the a power, then it's going to be x to the a over r. So whatever number your root is goes on the bottom of the fraction. Whatever your x is raised to goes on the top of the fraction. And in this case, x is not raised to a power, so what power is there? 1. So for this one, Wesley, what would we get whenever we do that? 1/3. Perfect. I think this right here is one of those things that we probably kind of lost during COVID. I think it may be one, because I remember last year with pre-cal that nobody really knew how to do that very well, and I glazed over it in pre-cal, but it may not have stuck. So this rule right here we want to be familiar with, because we'll use it a lot where it is a lot of times for us easier to deal with fractional exponents than it is to deal with the roots. So we'll use it quite a bit. But this is not our derivative, right? This is just rewriting it so it's x to a power. So Wesley, what will we get when we do the derivative?
1/3 x.
Good. And then what do we have to do to that exponent? We don't flip it. It's the same as it is when you're doing like 9x to the 5th, right? You multiply out front and you get 45, and then what do you do with your exponent right there? subtract 1. So it's the same thing here, it's just a little harder to do. So we're multiplying out front. There wasn't anything out front, so we just get the 1/3. And then we're going to do x, and then we're going to do 1/3 minus 1. Right? So 1/3 minus 1, you got to get common denominators there. So you got to multiply by 3 on top and bottom. So you're subtracting 3 over 3. And then we'll get -2/3. So we get 1/3 x to the -2/3. Okay, so it's a little harder to do than it is whenever you just have 5, right? But it's the same thing. Multiply out front, subtract 1 from your exponent. Also, they may not leave your answer like this. This is perfectly fine if it doesn't specify. They might move that exponent down to the bottom and make this 1/3x to the 2/3. It's possible because that negative exponent might go to the bottom. And then it is also possible that they might change that back to a root. So we'd have a 3 right here. The root is on the bottom of the tree, right? So roots are on the bottom of a fraction, so it would be the cube root of x squared. Again, any of those 3 are perfectly fine. Free response, I'd leave it here unless you need to do something else with it, but any of them might show up on multiple choice too. Okay, questions? Okay, example 5, ask us to find the slope of the graph of f of x equals 3x to the third minus 4x squared at 1, 0, and -2. So, Raven, whenever it says slope of the graph, what is it looking for? Derivative, right? So when we see slope of the graph of f of x, we are thinking derivative. Right? So this would take forever the way that we were doing it before. We had to do limit definition of a derivative. But now it is so much easier because all we have to do is take our derivative using that power rule. So when we take the derivative of this, Raven, what will we get? 9x squared minus 8x. And then if we want to know that derivative at those points, we just have to plug in the number, right? So we would do f prime of 1 would be 9 times 1 squared minus 8 times 1, which would give us 9 minus 8, which would be 1. If we plugged in 0, we'd get 9 times 0 squared minus 8 times 0. And that's just going to give us 0. And for our last one, f prime of -2, we'd have 9 times -2 squared minus 8 times -2. And so that would be, make sure, what have I got to do first here? The 9 times -2 or the -2 squared? -2 squared, make sure you do the exponents first there. 9 times 4 plus 16. So we got 36 plus 16. And we're going to get 52 for that one. So if you're looking for slope of the graph at a specific point, just plug that number into your derivative. All right? Okay, and let's do a tangent line problem like we did on the warm-up here. So tangent line problem, there are 3 things that I have to have. Connor, what are those 3 things? Good. And your equation, right? So slope, point, and equation. Wonderful. All right, what do you want to find first, Connor? Okay, so to find the slope, what do we need? Good. And so right now, f of x is not just x to a power. So how can I rewrite that? X to the negative 2. So that's not my derivative. But I'm going to take the derivative. And what will I get, Connor? And for the purpose of plugging numbers in, it's going to be easier to do if you take that x to the third and send it back down to the denominator. Because otherwise you're thinking, what is x to the negative third? Which you're probably just going to need to move it back down to the denominator anyway. So this is my derivative. I have it clearly labeled as f prime of x. So that is my slope at any point. I specifically want the slope at x equals 1, so I'm going to plug that in. So I got negative 2 over 1 to the third power, which is just going to give me negative 2. So here's my slope. All right, so check. We've got that. Okay. Grace, how are we going to find the point? Okay. If we ever need a point on any graph and we have one of the coordinates, we just plug that into the original equation. Okay. Not the derivative, because the derivative gives us the slope, right? If you need a point on a graph, you just plug into the original. So we know x equals 1. So we're just going to say f of 1 equals, it's better to use the 1 over x squared for this because it's just easier to deal with than x to the negative 2. So 1 over 1 squared. And Grace, what do we get for that there? Just 1. So our coordinates of our point are going to be 1, 1. Okay? So whenever we find the slope, we're looking for f prime of 1. When we find the point, we're looking for just f of 1. And then our equation, we're just going to take these 2 things we found and throw them into our point slope form. So for our equation of tangent at x equals 1, we're just throwing these 2 things in to this form. So we've got y equals, the slope is negative 2, and then we've got x minus our x coordinate, which is 1, plus our y coordinate, which is also 1. And so this is what we're looking for. Unless they specifically ask you for something like the y-intercept, don't do anything to it. Just leave it like this. Because there is a chance you might mess it up simplifying. Hopefully you won't, but you could. So I would just leave it. Okay, so this one, you know, those of you, I might be emphasizing it too much, but these show up a lot. Slope, point, equation of the line are the things you're looking for. So for the slope, you got to find the derivative at that point. For the point, you just plug into the original equation and then use that for your equation of a tangent line. Okay, those are 3 things. These show up a bunch. So you will definitely see these a lot. Okay? Okay, let's do one of these. Those of you in physics will appreciate this, maybe. Possibly. this formula here, we actually do this in Math 1. I don't know if Miss Ball did the pumpkin chunking with you guys. Did she do that with you guys? Or where you did the pumpkin chunking problems? If you did, you've seen this formula before. I usually do it with my kids in Math 1, but I didn't have any of you guys for Math 1, did I? No. So even though I haven't taught semester in a while, the likelihood that Foundations kid makes it to calculus is usually, or makes it to calculus while still in high school is usually low. I have had one. She did make it. So this formula here gives the height of a projectile after a certain amount of time, right? And in this formula, I'm going to give you what a couple of these things stand for. That V sub 0 right there. In those of you that are in physics, when they put the sub 0, what does it typically mean? Initial, right? And V is for velocity. So V sub 0 is initial upward velocity because we are only looking at height here. It's not like, it's just the upward velocity. All right, and then the H sub 0, it's got a sub 0 on it as well. So it is your initial height. And then T is going to be time. And to use this formula, it has to be in seconds. And and there are 2 T's in our formula. And the H is your height. And to use this formula, it has to be in feet. Do you guys use this formula much, or use meters per second? Yeah. Yeah. So typically a lot of science is going to use meters rather than feet per second. But I just use this one because it was readily available in my mind because we do it in Math 1. But it's a very similar formula. You can make the same formula that negative 16. It's just going to be a different number. I think it's like 5.9. Whenever it's, is it 5.9 if it's, I can't remember. So this is time in seconds, height in feet, and only applies on Earth, ignoring air resistance. Okay, go to the moon, gravity's different. It's not going to apply anymore. And you're ignoring air resistance. So you would only want to use this when considering a dense object, right? So a pumpkin, relatively close enough to use. You would not want to use this if a feather is launched into the air, right? Because there's an incredible amount of air resistance on a feather, and this equation would not even be close. But if you are looking at pumpkin, cannonball, something that's fairly dense, it's going to give you a decent answer, depending on how you look at it. So we have a pumpkin is launched from a height of 15 feet with an initial upward velocity of 60 feet per second. So the first thing I need us to do is just to write our equation. So our equation, I'm going to write it down here because I've written all this out and ran out of room. H equals negative 16 t squared plus 60 t plus 15. So if we think of graphing that equation right there, we know it's a parabola that's upside down. It's going to look something like this, right? On our x-axis, what do we have? Time. Our t, right? Specifically in seconds. And on our y-axis, what do we have? Height. In feet. So if I want to know the speed is going to be in feet per second. Speed is the slope of this graph, right? So in order to find the slope of that graph, at a specific point, I could take the derivative, but this didn't ask me for the speed at a specific point. What did it ask for? Average speed. So what we need to do is we need to find the slope just between the two endpoints that we're dealing with here, right? So we got t equals 0. So whenever t equals 0, we are just going to get 15. And so that's the point 0, 15. That's this point right here on our graph. And then we also need to know for t equals 1, because it's asking from 0 to 1 second. So we'll have negative 16 times 1 squared plus 60 times 1 plus 15. And that's going to be 75 minus 16, 59. Is that right? I think. So 159. And that is a point somewhere around here. Right? And if we want to know the average speed, we need to know the slope of the line between those 2 points. So for average speed, we do not use the derivative because we want to know the slope between 2 points that are far away, not the slope at a specific point. So we would say 59 minus 15 over 1 minus 0, and that is going to give us 44 over 1. So 44, what are our units? Feet per second. So average speed of the pumpkin from 0 to 1 is 44 feet per second. Okay? But if they want us to tell the instantaneous velocity at the pumpkin at t equals 1. So I want to know the velocity exactly. Then we're looking for not this line right here, but we are looking for, run out of colors to use here, let's use some orange. We're looking for tangent line right there. So, instantaneous velocity of the pumpkin at t equals 1, we need to take the derivative of our equation. So our equation was h equals negative 16t squared plus 60t plus 15. I really would like this better if this was called h of t. Let's call it h of t. And so if we take the derivative of this, h prime of t, that's going to give us negative 30t. No, not negative 30. 32. Oh. Negative 32 t plus 60. For my physics kids, just so you're relating this, because you're doing algebra-based physics, but the formulas are all derived using calculus. So like if you take that problem that we started with, negative 16t squared plus v sub 0 t minus h sub 0, when you take the derivative of that, it's going to give you velocity, and you'll have negative 32t plus v sub 0. You guys are using metric, so your 32 is going to be a different number, but this should look like one of those formulas that you guys are seeing. It's like negative something here, t plus v sub 0 gives you your velocity at a point. And so if we want to know it 1 second, we need to plug in. So negative 32 times 1 plus 60 is going to give us 28. Is that right? Yeah, 28. And this is feet per second also. Okay, and if you look at my little graph that I put up here, does that look reasonable? If the slope of this line was 44, should the slope of that tangent line at 1 be less? It should. So this looks like a reasonable guess based on what I've got here. Although it's not a guess. It should be right. There. So here's an interesting question that you might actually want to know. Because let's say that an unfortunate individual is standing right here, and the pumpkin is about to hit him in the head, or I guess maybe he needs to be laying on the ground, so it's actually at the ground for this to be the case, or we'll consider his height negligible. We might want to know with what force he's getting hit in the head, and we'll need to know the speed of that pumpkin. Mm-hmm. Yes. Yeah, that's what we're going to have to do. So we might want to know, or we may just want to know, like, how fast is this pumpkin going? What kind of damage is it going to do to the pumpkin, right? Now, obviously, if we're dealing with pumpkins, we might not really care about all of these things. But you can imagine other contexts where something different would be important. So we first need to know when the pumpkin hits the ground, right? So what is the height of the pumpkin when it hits the ground? All right, 0. So we know that the height would equal 0. So in that formula, h of t equals negative 16t squared plus 60t plus 15. We know that at the ground, h of t, the height, is going to be 0, right? So, so that would look like this. 0 equals negative 16t squared plus 60t plus 15. And there's a chance that that factors, but I doubt it. And even if it does, I don't want to deal with it, right? So what's our other way we can deal with solving these? All right, sing it for us, Connor. So, quadratic formula is going to come into play here. We're going to use our quadratic formula. So, negative 60 plus or minus square root 60 squared minus 4 times negative 16 times 15 all over 2 times negative 16. I'm deeming this calculator active right here. So you end up with negative 60 plus or minus square root of 4,560 over negative 32. I like to simplify what's, you can technically type this all in at one time, but I like to simplify what's in the radical at least first, because it makes it easier to type it in. Let me grab my calculator. when you type this in, you either need to do it this way, negative 60 plus square root of 4,560. Hit enter. Here's the problem with the 89. It's going to simplify that radical for you, which could be nice if you were having to like do this. But if we want a decimal, we're just going to hit green button, enter. And then I need to divide that by negative 32. So this gives me negative 0.235243. Is that what I want? No. I've got two x-intercepts here. One of them is the negative one. It doesn't apply to this situation, right? What I'm looking at here is that what I just found is this point over here, which does not apply to what we're actually doing. So let's try it with the, that was with the plus, so let's do negative 60. Actually, I'm going to do it all at once this time. If you type this in all at once, you have to have parentheses around the numerator, and you can get by without having parentheses around the denominator because it's a single number here, but if it were more than one thing, you would need to have it there too. So negative 60 minus square root of 4,560. You have to close the parentheses for the square root, and then you would have to close the second parentheses for the top of your numerator. So you got to be careful with parentheses whenever you do this. And then divide by negative 32. I'm going to hit the green button, enter. So I get 3.98524. So I guess really this is a T right here. What was it? 3.9824. Keep that in your calculator. In fact, it may or may not be helpful to do this because you might just be able to use the answer key. But you can store values on this calculator. So when you have this number, 524, wasn't it? When you have a number and you know you're going to need to use it again later in the problem, you can store it. So if you just click the STO button right here, it's right above your own key. You can store it as any letter. Please don't store it as X because it can cause all kinds of havoc if you store it as like X, Y, Z, T. Don't use those letters. So I'm just going to store this as A here. So now anytime I type A, it thinks A is that letter, or is that number right there. So I can plug that back in. You may end up just being able to do it with that second negative key that brings your answer back up. But sometimes you might have to do something else first, so this is helpful. You also can go up on these and highlight an answer that you had and hit enter, and that'll bring the whole decimal down. So those are both ways you can deal with that. All right, so we're not done here. That is the time when the pumpkin hits the ground. But what did the question ask us? Velocity when it hits the ground. So velocity means we need to plug into h prime of t, right? That's our velocity here. So h prime of 3.9824524 is going to be negative 32 times 3.98524 plus, what was it, 60, right here. So we're going to do negative 32 times, you can do second answer, since I stored it, you can do A, you can go up here and highlight that value, any of those, but don't use the rounded value. And we get negative 67.5278. And that is feet per second there. Why is it negative? it's going down. Velocity has direction. So if it's positive in this case, it's going up. If it's negative, it's going down, which is what we should expect when it hits the ground, right? It should be going down. So the pumpkin, if this unfortunate person is standing in the path of the pumpkin, it is going to hit them at 67.5278 feet per second. I do not know what kind of physical damage this will do to a person, but I bet it won't feel good. Okay, questions? All right. You have some stuff on like sine and cosine and e's and stuff. I did not mean for that. I took that off of these notes. They go on tomorrow's notes. So we will do that whenever we get there. So that stuff is not right. Also, the assignment you have at the end is probably not correct either. So the assignment, and you got about 20 minutes to work on it. It is a lot of problems, but it should not be one of your longest homework assignments because this is just power rules stuff. So 3 to 17 odd, 25 to 29 odd, 39 to 47 odd, and then 56 and 57, or 55 and 56. So everything's odd except for that 56 at the end. And these should go fast and be ones you do not have to show a lot of work for most of them. Oh, there's one type of problem I forgot to tell you. If you've got x to the 5th minus 3x squared plus 7x squared over 3x, we do not know how to take the derivative of that because it's got a fraction. But what could we do to make it so we can take the derivative of it? What? Factor out of x and cancel is one way that you can deal with it. So you could factor out of x and cancel. So that would look like this. X to the 4th minus 3x. Well, I meant for one of those. Let's make that x cubed. X squared plus 7x over 3x. And you could cancel. What would we do with that 3 in the bottom? The other way you can do it besides factoring, because you're going to eventually have to do this with the 3 anyway, so I would suggest this, but factoring is a good idea, is you could do the love connection here. Don't go to college and tell your professors that you did your love connection on the problem. They will probably laugh at you, especially if you have a very serious professor, but helps me remember, right? The love connection is just where we divide all of the things in the numerator by whatever's in the denominator. It's called the love connection because if you just have 2 of them, it makes a cute little heart. But you divide everything by what's in the top, so that's going to be x to the 5th over 3x minus 3x cubed over 3x plus 7x squared over 3x. And so what should happen on your work here is you're going to have one of those cancel, and then you would get, this has a 1 with it, so we could write that as 1/3 x to the 4th minus 3 divided by 3 is just 1, so we just have minus x squared plus 7/3 x. So if you run into a problem like that, where it looks like it's a crazy fraction, at this point in the homework, you should be able to do the love connection. Now, we will learn how to deal with it on ones where you can't do the love connection eventually, but not yet. And that's not your derivative, that's just your function still. You would still have to do x plus 4 to the 3rd, x to the 3rd minus 2x plus 7. Okay, so you got about 20 minutes. Try to get as much done as you can. Hopefully you can get most of it done before you go. These should be hopefully fairly quick.